Hey everybody, what's going on? Welcome to our officially second to last, I believe, video lecture. Since I said that, I'm probably going to screw that up somehow. I imagine it's going to somehow propagate. We're going to have like 100 video lectures left somehow. I apologize, but you don't have to listen to my voice too much longer. You guys did a great job so far this semester. You still have room to screw it up on the final. But regardless, we get to talk today about one of my favorite topics, which is environmental physiology or extreme physiology. There's a bunch of stuff here that we can really go into. Like, I don't know what I just did with my breathing. There's a lot of stuff here that we could really go into, right? Like we could talk about space flight, we could talk about altitude, we could talk hyperbaria or deep sea diving or what happens in when it's really, really hot out or really, really cold out. Unfortunately, most of those physiological phenomena are going to be that kind of sounded funny. Most of these arenas in which you might be seeing humans frequently are going to be a little bit less common. So we're going to today focus on the ones that are more common, which are going to be altitude, heat, and cold. If you guys want, we can talk more in class or we can talk in person, just kind of one-on-one about some of these other really neat areas of extreme physiology or environmental physiology. But without groaning on too much and wasting too much of your time, let's talk about altitude, right? So essentially what it comes down to with altitude is that we are changing atmospheric pressure, right? When we go from sea level to the top of Mount Everest, what we are doing is we're changing atmospheric pressure. We're changing the partial pressure of oxygen. With me saying that right now, you should already be thinking about how that is going to affect physiology, and you should already know that answer, but we're going to go through it anyways. There's a couple of key terms that we need to talk about here. So the first one, atmospheric pressure, is going to be the total pressure of all the gases inside of the atmosphere. Just because it's a change in pressure doesn't mean that there's a change in volume of air, right? Like it's not like when you get up to the top of Everest, there's no longer air. It's just that the air is thinner. We will talk about that. We already know what our partial pressures are. That is, what is the pressure of each individual gas within that entire atmospheric pressure? So what's the partial pressure of oxygen, nitrogen, carbon dioxide, carbon monoxide? You guys guessed it, xenon, right? All those gases are going to play into a role here. Hypoxia is any time that there's low partial pressure of oxygen, low PO2. That can be at altitude. That can be simulated with asphyxiation. We can simulate that by restricting our breathing. However we want to do it, we can actually significantly affect hypoxia. Normoxia is normal partial pressure of oxygen. Go figure, right? Normo, makes sense. And then hyper, you guessed it, high levels of oxygen, high partial pressures of oxygen. I'm never going to ask you guys to know these values over here on the right, but I want you to pay attention to is that as the altitude goes up, the partial pressure of oxygen goes down. As the altitude goes up, the partial pressure of oxygen goes down. If you remember all the way back to when we were talking about respiration and ventilation are going to be driven by pressure gradients and pressure differences. This is going to be huge for us, right? We'll talk a little bit about Everest today, which is kind of cool. So what does it mean that we have a low partial pressure of oxygen as we go up in elevation? What does it mean that our partial pressure of oxygen gets lower? Well, it creates this concept of thin air, right? Into thin air. We are essentially minimizing the concentration, right? The density of the air. So as we're moving from sea level towards higher altitude, it's not necessarily that we're eliminating the oxygen or removing the oxygen from the atmosphere. What it means is that we're actually disbanding or spreading out the oxygen. So there's not as much oxygen per unit of measure. So it's actually thinner, right? Like it's not as dense of a gas. So there's not as much room for onloading or offloading. So as you increase with altitude, you're actually going to decrease the partial pressure of oxygen, which is going to decrease the amount of air or oxygen that we're able to bring in and bind. You should automatically be thinking about the oxyhemoglobin dissociation curve. Yep, you guys' favorite best friend that we've ever talked about is making a comeback right now. So what we have with oxyhemoglobin desaturation curve is we're seeing how saturated our hemoglobin is. As we move lower and lower in partial pressure of oxygen, which is moving towards the left on that x-axis, we're actually going to be facilitating O2 offloading or minimizing the ability to saturate that hemoglobin, right? So as we decrease the environmental partial pressure of oxygen, we're actually going to decrease the ability to load oxygen. If we decrease our ability to load oxygen, we're not going to be able to unload as much oxygen, right? Brains. So if we're thinking anaerobic performance, what type of effect do you think this altitude's really going to have on anaerobic performance? Right? Like there's not going to be a ton. There's not going to be a massive effect. There's actually a potential that you might have higher performance depending on the length of your event or the type of your event because there's actually less air resistance. So true story, the Mexico City Olympics decades ago, literally decades ago, there was several individuals that kept breaking record triple jump and long jump records. And what they found out is that it was because Mexico City was held at such a high elevation, there was less air resistance. So these guys were able to make it 2 or 3 centimeters further than ever been done before, right? Math, science, cool. What about our long-term aerobic performance, right? What sort of effect, if we're minimizing the ability to load oxygen, what sort of effect do you think we're going to have on long-term aerobic performance or long-duration aerobic performance? Right, like we're going to actually hamper or minimize our performance, right? Like we're going to decrease our performance and our ability to perform long-term or long-duration aerobic events because we're not able to get that oxygen out of the system. We're not able to bring that oxygen into the system. We're not able to unload that oxygen at the muscle. We're not able to put that oxygen in the mitochondria, and we're not able to use electron transport chain, use Krebs cycle, use any of these things to actually produce the high levels of energy that we need when we're doing endurance activity. So at elevation, no real change in anaerobic measures, or no real change in anaerobic performance is a better way to put that. And there might be, there's definitely going to be a pretty big hamper on your endurance performance. Anyone that's been to elevation for a prolonged period of time, even for a short period of time, you can agree with me, it sucks, right? Like if you've ever hiked a 14er in Colorado, it hurts. So just to kind of show you guys the linear relationship between altitude and aerobic power, or VO2 max, right? Like those two words are going to be synonyms essentially. I want you guys to look over to the right-hand side. And as you can see, the percent of maximal aerobic power measured at sea level. So Mexico City is about 7,400 feet above sea level. And you're going to be working at about 90% maximal aerobic power. So your endurance performance, your maximal aerobic fitness level, your VO2 max, is going to be about 90%. As you move to Leadville, Colorado, which is where Western States Ultramarathon is going to be held, or into Nuna, Peru, into the Andes, you're going to start to see quite a drop off, right? Like 70% VO2 max is like, that's what you're going to be working at. You're losing 30% of your fitness, like right off the bat, technically, right? Like that is insane. There's massive shifts in aerobic performance. It's not just due to the change in oxygen offloading and onloading that's going to be occurring here. There's actually, at certain elevations, you're going to actually start to have changes in maximal cardiac output as well. So your VO2 max is going to reduce due to not just a change in AVO2 differences, but also a change in heart rate. You actually can experience a decreased maximal heart rate at elevation. So we just double whammied our VO2 max, right? Like we're now attacking the ability to get our heart rate up to maintain cardiac output, and we're attacking our ability to extract oxygen, which is going to put our VO2 max in the pooper. So let's look and let's kind of evaluate why this might occur, right? Let's go back to your second trusty friend, the side piece, the Fick equation. And that's going to be our VO2 max is equal to our heart rate max times our stroke volume max, or our Q, times our AVO2 difference, or our O2 extraction capacity. What I want you to look is that as we experience a decrease in partial pressure in ambient air, as we decrease the amount, the partial pressure of oxygen in the atmosphere, right? Like what I'm breathing in right now, what you guys are breathing in as well, we're going to decrease that when we move to elevation. And what you can see is that there's actually a significant trend line all the way through, right? Where we are actually significantly lower in oxygen saturation all the way through. And the partial pressure is going to be significantly lower all the way through. So it's not like our body has this ability to take this atmospheric Charlie Foxtrot and basically create a smooth interaction for us, right? We can't produce oxygen out of nothing. We can't saturate our hemoglobin out of nothing. We have to have this partial pressure of oxygen that can be maintained. And when we go to elevation, we can't do that. So we see significant performance decrement. So let's look at some of the more acute responses to altitude exposure or submaximal exercise. So again, the key word here is that we're looking at submax. We're not looking at maximal aerobic power or maximal aerobic production or maximal VO2, right? We're looking at submax exercise. And as you can see, as you transition from sea level to about 3,100 meters or 10,000 feet, you're going to see a significant uptick in our heart rate. And now remember, VO2 max is equal to cardiac output times a VO2 difference. If we're decreasing the partial pressure of oxygen, we're going to have to bump up that heart rate. We're going to have to bump up our stroke volume, or else we're going to lose that VO2. We're going to lose our ability to consume and utilize oxygen. So we have to bump up that cardiac output. And this is going to be achieved, at least in short, by bumping up the heart rate while we're doing submax exercise. What we're also going to see is we're going to see quite a bit of an increase in ventilation. So remember, ventilation is a mechanical process of bringing air in and out. We're talking bulk flow here, and we're trying to drive air in and trying to drive CO2 out. And what you'll see is that there's significant increases in ventilation that occur as we increase in altitude. So as we increase in work rate and as we increase in altitude, there's going to be significant increases in ventilation. Where this is not hyperventilation because we're trying to blow off all our CO2, what we are doing is we are gasping for air, right? Like we are trying to bring in as much oxygen as we possibly can because we're not able to grab as much from the environment per breath. So our efficiency of breathing has gone down. We actually have to increase the frequency of ventilation in order to bring in the minimum level of oxygen that we actually need to consume and utilize. Remember that the reason we do stupid stuff to our body is because it adapts. Just like our body adapts to resistance training, just like our body adapts to endurance training, our body will actually adapt to altitude. And it has a couple different levels of adaptations, right? Like there's chronic adaptations, there's more acute or short-lived adaptations. There's adaptations that people experience if they've lived their entire life at altitude, like Sherpas. Like elevation. See what I did there? There's going to be these adaptations that occur. One of the first adaptations, one of the primary adaptations is going to actually be that we're going to produce more red blood cells. We're going to improve our hematocrit. We do this a couple of different ways. One way is that our body is actually going to sense that we're running out of air. We have low air, and that's going to be done by HIF-1 alpha, HIF-1, and then it should be like a little Greek alpha. And HIF-1 alpha stands for hypoxia inducible factor number 1. And what HIF-1 alpha does is it serves as an oxygen sensor. Just like AMP kinase serves as an energy sensor, HIF-1 alpha is going to serve as our O2 sensor. When we experience those changes or those activations or those negative side effects of hypoxia and the increases in HIF-1, we're going to actually stimulate our kidneys to produce EPO or erythropoietin. If you're familiar with cycling as a sport at all, EPO is a massive drug. It's a huge performance benefit. It is one of the go-to drugs that these guys use to try to improve their performance. And what it does is it actually increases and stimulates the production of red blood cells. So we're actually going to increase the amount of red blood cells. If we increase red blood cells, we're going to increase the ability to carry oxygen. If we increase our ability to carry oxygen, we're going to increase our O2 saturation. Funny thing, that's going to be an adaptation to high altitude, is this ability to carry more oxygen or increase our O2 sat. One way is erythropoietin, right? Like we're going to increase the amount of red blood cells we have. The second way is we're actually going to put more blood through the pulmonary system. We're actually going to be trying to put more blood flow towards the lungs. We're going to control the way that the blood is flowing, and we're going to control transit times, and we're going to control everything to shoot more blood towards the lungs and try to allow for a greater diffusion of oxygen from the lungs into the blood. It's actually kind of cool. It's one of the primary adaptations to why Himalayan Sherpas are the guys that actually essentially summit Everest every single day for a job, are able to do what they do and do it so well. It's one of their primary adaptations. They've lived at altitude for so long that they've actually changed the way that their blood flows through their body. It's kind of cool. If you were to basically take these potential adaptations, increase oxygen saturation, increase red blood cells, increase blood flow to the lungs, what we've just done is we've improved our ability to carry oxygen dramatically. We've improved our ability to carry oxygen. We've improved our ability to saturate oxygen onto red blood cells. What we're going to do is we're going to maximize our ability to offload that oxygen, and we're going to maximize or increase our VO2 max, so we'll increase our performance. So there's got to be a training benefit to being at altitude, right? How can we optimize those adaptations? Well, one way is that we can actually train for competition at altitude. And this goes a couple different ways. So we have live low, train low. So we have live low, train low, which is basically saying you live at sea level and you train at sea level. You're not really going to get benefits from altitude there ever. There is live high, train high. So you live at altitude and you train at altitude. And there's live high, train low, right? And we'll go through the live high, train low a little bit more here. But what I want you guys to know is that the variation, there's a high level of variation among athletes. Not every athlete is going to be able to get significant performance benefits from live high, train low or live high, train high. It's going to vary. Some are going to be able to improve, some are not. Some are going to be able to increase their VO2 max or maintain that increase, some are not. It's going to be kind of like a shotgun spray. Well, let's talk at least about live high, train low, because one, I'm sure you'll see it as you move into this career field, but two, it's got some support to it, right? There's definitely a reason that our Olympic Training Center is in Colorado Springs. There's a lot of reasons why this would work. Essentially, what we're trying to do is we're trying to net positive all the adaptations. If we train at altitude, what is the problem? We cannot actually work at the high levels that we need to do in order to maintain performance or improve performance, right? If you go back to exercise prescription, our athletes, if we're working with athletes, they need to be training at an extremely high level in order to get further improvement. Same with resistance training, same with running. So if we take a period of time where we put them at altitude and make them train at altitude, are they going to be able to train at that high percentage? No, right? They're not going to be able to hit the numbers that they need to hit. They're not going to be able to get effective training like they should. But if what we do is we actually take and put them at altitude for long periods of time, say living there, and all their training sessions are just done at sea level where they can maintain performance, then they're going to get all the benefits of living at altitude and the performance benefits of being able to train in a high training zone, right? They're going to be able to actually train at a high level because they're not at elevation. So what it comes down to is it's essentially intermittent elevation. We're trying to maximize the response from training at elevation. We're trying to maximize or living at elevation and maximize the response of training at sea level. Super expensive. I mean, if you're a really good athlete, you might want to try it. It can be expensive. You'll see that some people try to replicate this by spending time in hypoxic, hyperbaric chambers. The research is mixed, right? We don't have great information on whether or not it's going to actually do too much. But they are extreme fire risks. So if you're going to do something like this, make sure you don't smoke in there or something. I don't know. Since we talked about performance at elevation, it's so crazy to not try to talk about some of the biggest mountaineering feats to ever occur. In 1953, the first successful summit of Everest was completed by Sir Edmund Hillary in Tenzing Norgay. There's actually an entire backpack company named after Tenzing. They're amazing individuals. Read their story. It's really a cool story. Up until this point, essentially, no one thought it was possible to even summit Everest, let alone summit Everest without supplemental oxygen. If you look on Tenzing's back, you can actually see that he has this supplemental oxygen. If you look at it, like they're wearing like World War II era gas masks, it's kind of crazy. So no one thought that'd be possible to actually summit Everest without supplemental oxygen. There was actually some very bad math done at some time where they thought that the barometric pressure was significantly lower than it really is. Essentially what it ends up equating out to is that your absolute highest VO2 max that can occur at elevation is about 15 mLs per kg per minute, right? So your max is 5 mets. So that's not even an aggressive, that's vacuuming the floor. Like that's 3 to 5 mets. So imagine trying to hike up a mountain and that is your maximal capacity. It's like you're maxing out at vacuuming the floor. Incredible feat. Reinhold Messner and Peter Habeler both completed the summit successfully in 1978 without oxygen. Insane. Unfortunately, nowadays, it's like everybody and their mother is summiting Everest. In case you haven't seen, I don't know how you wouldn't have seen, there is literally a backlog of people stuck on the summit of Everest trying to just summit and get back down. People are literally dying, standing in line trying to get to the summit of Everest. Because if a storm comes through, like you can't go forward, you can't go backwards. They're cattle just being herded around on the summit. Like it's no longer as incredible of an achievement as it used to be, which is sad. Just a little bit more mountaineering information for you guys, because I know a lot of you like to be outside. You can see that realistically from 1900 to about 1978, where Messner and Habeler actually made the summit of Everest without supplemental oxygen. In that like 70-year time, there's been some pretty impressive accomplishments. And in fact, there was 4 or 5 different summits of Everest completed with supplemental oxygen before the official trip up the top of Everest without supplemental oxygen. It's just cool. Because it's extreme physiology, we need to talk about what does VO2 max look like at these levels, right? Like I already said, it's 15 mLs per kg. And that's insane, one, but let's look at kind of what that looks like, right? So at sea level, if your VO2 max is 60, which is actually high, it's a fairly high VO2 max for most individuals. You can see that summit of Everest actually ends up being about 15. And what this is there was 2 different physiological experiments that were actually funded to go do research on Everest. So there's Pugh et al. In 1964. This is when it got published. I believe they summited, or they hit a camp, that a high elevation camp. I don't know that they actually made the summit officially. In 1962, don't quote me on that. I think that's the truth. And they actually did a series of physiological experiments. So they actually did exercise science, exercise physiology experiments on the mountain, which is really cool. And then the 1981 expedition, they actually made it to the summit and did some physiological testing at the summit to see what VO2 max looked like. Like that's talk about a cool freaking research study. All right, next video, we're going to move into heat injury and start discussing some of the vectors of injury and some of the side effects of heat. This one's probably a little bit more applicable to you guys because we live in Georgia where it gets hotter than a hoochie coochie. Thanks, Alan Jackson. And we'll see you guys in the next video.